nice August Friday, but hopefully we'll keep you entertained for a little bit with the learning, with the outcomes of this summer course. So AOS 404, for those who don't know, is our meteorological measurements course. Every year we try to find ways we can integrate experiments and measurements into the curriculum using this course. Some years we design our own, other years we piggyback onto existing experiments. This year was particularly fun for me because we just, had the course run over the summer for the first time. So way better weather conditions than previous students who've taken this in other years, trapped in blizzards in Colorado places. And we also got to be embedded with a field experiment that I'm leading, which is this CHEESEHEAD project in northern Wisconsin. And a number of people in this room are also involved in that project as well. And so what I had suggested to the students was to come up with a way you could tap into the experimental domain where we were working with and ask an interesting question that wasn't being asked by the core experiment. And I think we'll hear more about that. And the title here, dubbed CHEESEHEAD Junior. Though I think many of the folks here have enjoyed quite a bit by the hard work that came through this experiment and really learned that maybe that junior title is maybe a little bit of an underappreciated. Title is Investigating Small-Scale Training Meteorological Influences on Atmospheric CO2, and this is being presented by Juliet, Peter, Jess, Sophie, Iman, and James here, who is currently in the field in the CHEESEHEAD domain, working over the summer as our research intern. So since he's needed up north, he's presenting remotely as well. So I'll turn it over to you. Thanks.
All right, awesome. Thanks for coming. We can go to the next slide. We've already been named by Professor Desai, but we'd also like to thank everybody who helped us throughout this project. It's been an extended effort, but we're pretty proud of what we've come up with. And we'd also like to give a shout out to Fran, who's probably the best companion we could ask for throughout the field work.
All right, James, go ahead.
All right, so CHEESEHEAD is an intensive research project with Ankur Desai as the lead PI, and it's designed to look at problems regarding the boundary layer and its responses to the surface atmosphere heat and water exchanges. CHEESEHEAD runs from early July to mid-October and has 3 intensive observation periods. And it was during this first intensive observation period when our class conducted our CHEESEHEAD Junior. CHEESEHEAD consists of 19 eddy covariance flux towers surrounding the long-standing WLEF tall tower in a 10 by 10 kilometer domain. Many other organizations and groups are also involved, including NOAA, NCAR, Montana State, the Karlsruhe Institute of Technology, UW-Milwaukee, University of Wyoming King Air, and then NEON. And the goal of CHEESEHEAD is to address the missing portion of the energy balance present in models, as well as be able to address the scaling problem as a result of surface heterogeneity.
Okay, so for the motivation, so as Ankur was saying, we were trying to come up with a question that wasn't already being asked in the CHEESEHEAD field project. So we were thinking, so CO2 is a very modern and very relevant issue right now. And the second thing that we had to consider was the location that we had access to. So the national forest that we were studying is very large and very free of anthropogenic emissions or really influence. So we thought we could do something measuring CO2 and how it interacts with like our location, our vegetation, stuff around us like that.
Yes. And as well, the Schwalmingen National Forest and the WLEF tall towers have been used for decades to study carbon dioxide. Some of the more prominent studies being how these concentrations vary with frontal movement, surface fluxes, and various types of vegetation in the area.
And just to point out, we kind of have the poster child for CO2 in the atmosphere with the Mauna Loa Observatory, a very famous and very prominent figure. So James.
All right, so what we really wanted to look into in our experimental questions were how does CO2 concentrations change over various kinds of terrain? And then we also were wondering, does meteorology impact that relationship? And so then we decided our hypotheses are CO2 will not vary across terrain, but will vary with meteorology, such as relative humidity, temperature of the air, or wind speed, or CO2 will vary across terrain with meteorology, or CO2 will vary across terrain, but mainly as a result of vegetation.
Yep. And so with those hypotheses and questions in mind, we headed out to the field. So on July 7th, bright and early, we packed up our 3 vans and we headed up actually first to Rhinelander, where we were actually able to go inside the University of Wyoming's King Air aircraft. That was a really cool experience. It wasn't really relevant to what we were doing, but it was an added bonus that we got to do. We also saw a hodag, very famous in Rhinelander. And then we headed up to the Kemp Natural Resources Station, which is actually owned by the University of Wisconsin-Madison College of Life Science and Agriculture. So once we arrived to Kemp, which is right here from above, we had 6 days that we were in the field, that we were able to take data. We took the first day as kind of our dry run, our test, kind of get our bearings in the field, launch a balloon, see how that went. So we ended up with about 5 days of data that we used.
So these were the instruments we used in our experiment. We used the Picaro gas scouter to measure the CO2 concentrations. We used windsondes to calculate mainly wind speed and wind direction so that we were able to calculate a second launch site. And then we used the Tough Book for recording that data and receiving it real time. And then we also used the Tall Tower for more data analysis afterwards. So the Picaro gas scouter records ground level CO2 concentrations, and we would run that at our first launch site, and then we'd also run it in between the first launch site and the second one, and then also at the second one, so that we got a thorough data of our entire area that we were covering. The windsondes we used to find wind speed and direction so that we were able to track which way the wind was going so that we could potentially follow that air parcel as close as we could. And we also used that to kind of scope out the terrain and find, like, if there was a marsh or a pond or something nearby, we would try to pick more like interesting terrain so that we could use that in our comparison. We use CO2 concentrations at different frequencies for our data analysis, and the National Weather Service reports we also use for some of our meteorology analysis.
And just to mention, this is the WLEF Very Tall Tower, which is in the forest that we're studying. It's about the same height as the Willis, or formerly Sears Tower in Chicago, so it's very tall. So the game plan. So like we mentioned before, we were trying to look at CO2 concentrations as they move across a landscape, particularly one with lots of varying vegetation. So our initial plan was to try and take a CO2 concentration at our initial site and then sort of chase that air parcel as it moved along the landscape, which ended up to be a little bit more difficult than we had thought. We figured out we can't really chase the air parcel as quickly as the air was moving above us. So we modified our experiment a little bit, and we tried our best approximation to where we think the air parcels following the air parcel we took would be. So it's going over a similar patch of vegetation and terrain.
Yeah, and so to distinguish the meteorological versus the terrain influences on CO2 concentration, we calculated surface CO2 fluxes, and that could help isolate what is being contributed by the land. And we used the boundary layer heights that we detected from the windsonde potential temperature profiles that we calculated to apply to our surface CO2 fluxes.
And then actually changing up gears a little bit here, I have an interactive map that should give you a little better idea. Yeah, I have the tab open, I'm just not able to see it where it's...
Try it. Is it F11 for full screen?
This is how it goes with presentations sometimes.
We can see the tab, so we can, if you look it up.
Oh,
Okay,
okay, guide me.
Okay, up. Just a little bit more. Okay, now, click.
Am I there?
Yeah, click. Did we move a little bit more up and click?
There we go.
All right, yeah, all right, we got that. All right,
Audience participation.
thank you, everyone. Now part of this presentation. All right, so this was the part of the Shagamuguan Mikula National Forest. I have trouble with that name every time. It's all right. So this is actually just one part of about 3 that encompass this entire national forest. So just taking a closer look, so you can see where we were in this, like we're in northern central Wisconsin here. Taking a closer look, so this is actually the CHEESEHEAD domain. So each green dot that you're seeing represents one flux tower from Ankur's research that's going on up there. The bullseye that you're seeing is actually, it's called the Iss Field Site, and that's where we would do our daily launches every day. Moving into our own project domain, so the white dashed box that you're seeing is about the area that we covered with our Winsons and Picaro concentration. Taking a little closer look at where we were. So that clearing that you're seeing with the bullseye is the ISS field site, and just to the right, you're seeing the WLEF very tall tower, which is hard to see from above. So going into, this is a conglomeration of all of the Winson paths that were taken during our entire research period. You can see we had lots of different prevailing winds throughout the week, so we're actually able to get a good sampling of our project domain. So this covers about 165 square miles of forest, which I found pretty impressive for this kind of short, small scale research project. And that's the area that we covered within our project domain. So if you take a closer look at these paths, for example, this is Thursday's path. The solid line that you're seeing there represents our initial balloon launch, so that's where our first Winson headed. We used that data in real time to try and find a secondary site where we were going to measure our secondary concentrations with the Picaro. And this is actually an interactive map. So if you click on the solid line, it'll represent all of the vegetation that's underneath to help us kind of quantify what vegetation or what land cover is going to affect CO2 the most. You can also click the red X, which is where we took our secondary concentration measurements, and that'll show you all of the Picaro's CO2 concentration for the day. So a link to this will be available somewhere. We'll have to figure that out, but it's definitely worth taking a closer look at. It has each individual day sectioned off, so you can see the different prevailing winds that were pushing the Winsons, in this case, east. So those are definitely worth taking a closer look at. All right, now I'm gonna need some help to get back to where I was going.
You're right on it.
All right, I'm going for it. All right, thank you.
So this was our typical experiment schedule. We left around 8:30 every morning, and it's about an hour drive to our ISS site, where we would set up and launch our first Winson while we took CO2 measurements. And then once we were all wrapped up with that, we would send out 2 groups. One group would go retrieve our first Winson, They would use the Tough Book and the GPS coordinates that were provided by the Winson, and go out into the woods or the marsh or wherever, try to listen for the beeping. There was a few rough retrievals. And then the other group would go to the downwind area that we would calculate with the wind speed and direction and do a second launch, and also take more CO2 concentration measurements, and then also retrieve the Winson if it was possible. And then we would all meet back up at ISS for lunch and to talk about how our individual groups went. And then we would go back to camp and talk about our day and do a little bit of data analysis.
Okay, so what do you guys want to play on there? So this is just a video that we took to show you what a Winson launch looks like. Yep. Alright,
We're good?
that gives you a little better idea of what the ISS site looked like as well.
Basically, the drone under a list of instruments.
Peter's instrument.
For data analysis, we looked at trends in the weather conditions as well as the types of vegetation, the CO2 concentrations, and CO2 fluxes.
All right, and then as far as how the rest of this presentation is going to go, we're going to go through day by day, focusing primarily on days 3, 4, and 5 of our field research, as those have some more interesting things about them. But first, we're going to look at the maps as well as the weather conditions we experienced throughout this week.
All right, James.
All right, so I've been doing a lot of work with ArcGIS this summer. So I also plotted the Winsons. So that's just a quick map again, so you can kind of see just really how expansive our project went over the Park Falls district of the National Forest. And then if we go on to the next slide, so what we have here is the map of the initial and final sample locations, the straight line drawn between them. And to gather vegetation data, we received a plot dominant vegetation types from the U.S. Forest Service, and laying that plot over the map shown here, I plotted points at every 50 meters, starting at the initial location, and then spatially applying that data to the vegetation type. Being unable to travel along that straight line, both with the Picaro or to determine the vegetation in between, this method allowed for us to retrieve a generalized idea of what grew in between the Picaro measurements, so we can get a better idea of what caused these a change in the CO2. And then in the next slide, you can actually see the vegetation that was in between points and what really made up the land that we're saying caused that change in CO2, or potentially caused that change in CO2.
Yep.
So the weather conditions were relatively consistent throughout the week, except for a thunderstorm one of the days. So we decided to hone in on certain days that were more interesting than the rest. So some days that we didn't cover thoroughly in this presentation, but will be covered in our paper, are Field Day 1 when we went to Hay Lake, and Field Day 2 at Newman Springs. So Field Day 3 was at Winter Green.
So just to give an idea about what the weather was looking like, about like half a day beforehand and then leading into our launch times and after. So several hours before we launched, which was at typically around 10 a.m. every morning. So several hours before this certain day, there was a cyclone. So you see the cold front right here. Ah, perfect. Yeah, so there's a cold front, so during launch time, we are in the wake of that cold front, so there was a lot of cold, dry air during that time. And then, next slide, thanks. So then, looking at the meteorology between the sites, this is just a table of the temperature, relative humidity, and wind speeds for our first measurement site, which was at ISS, and then second at Wintergreen, and these values are just averaged over along the windsong, the windsong profiles. If you could go back, please. So for the most part, meteorology was consistent between these two sites. And then looking at how the boundary layer was interacting, we see that for both profiles, it's relatively well mixed because it's near vertical. Going up. This is a potential temperature, it's cut off, but potential temperature on the x-axis and height along the y-axis. And then the boundary layer was around 1150 meters above ground level from here. And go on to the next slide.
Okay, so the dominant vegetation type in between ISS and Wintergreen was predominantly aspen with some lowland conifer. And the Picaro measurements at Wintergreen had the lowest standard deviation and range of CO2 concentration, the largest compared to the other sites.
All right, and then looking at the actual CO2 measurements for the day, ISS started out at about 406 parts per million at the bottom, and then as the boundary layer stayed the same height throughout the morning, you can see on the left in the tall tower measurements, the high 396 meter level stayed relatively consistent. It was about a tenth of a parts per million change throughout the day. And on the right here, you can see the length of time that we measured the carbon dioxide for. And we also have a lovely instrument here on the end, but that's incredibly important.
It's part of field work.
All right, so like Iman said, that there was a difference in CO2 concentrations between our two measurement sites. And so in order to distinguish what exactly is contributing to these differences, in order to try to isolate between the vegetation and the meteorological components, we can look at the surface CO2 fluxes, and that can isolate the vegetation influence. So the equation for CO2 flux is equal to the change in concentration over time times the boundary layer height, which we got from the windsong profiles. And then, so the change in CO2 concentration is what we measured from the Picaro at both measurement locations. The time is the time between each launch of the windsongs. And so then, the typical value for noon and mid-latitude summer is about -20 micromoles meters or per meters squared per second, which indicates that at around noon at that time, the land is actually a carbon sink, and so there's a lot of net uptake. It's, through photosynthesis, it is using up a lot of the atmospheric CO2. And so this is around the time of launch that we did each day, and we see that CO2 is, or the concentration of CO2 is decreasing around this time. And this is just an example, but our next slide is from day 3. We used the atmospheric CO2 for at WLEF tall tower, again, to look at the CO2 difference, and we do see that there is that decrease between our two launch times. And then calculating, or the eddy fluxes at the WLEF tall tower gives the CO2 fluxes, and we do get a negative value, so that would indicate that land is a sink. However, that is taken at 122 meters, so not at the surface, whereas our Picaro measurements at the surface, we calculated, had a surface flux of 142.5, which indicates a really large carbon source. at the surface.
Day 4, we were at Patterson Lake.
Yeah, and so then the synoptic conditions for Patterson Lake was that it was at an onset of the storm, which means that there were going to be thunderstorms in the afternoon, and then people have to move next. Yes. So then, again, between both sites, the meteorology stayed relatively the same. As far as the boundary layer goes, there was a shallow inversion at both ISS and Patterson Lake. And then the boundary layer was at 1250 meters above ground level. So we didn't see as well mixed of a boundary layer as we did in the previous day.
And the dominant vegetation was red pine, and there's some aspen and hardwoods along the path as well. The standard deviation or range of the CO2 from the Picaro were similar to other days.
All right, and then as far as the carbon dioxide measurements go, it was significantly lower than the day before by about 5 parts per million. Patterson Lake was only a little bit higher, but throughout the day at the tall tower, there was a 5 parts per million decrease in the concentrations as time went on.
And so then looking again at the CO2 fluxes, this time you were seeing a slight increase in concentration between the two launch times. And this is indicative by the CO2 flux at the WLAF tall tower, although it was negative both previous hours. But then Picaro was showing a much larger CO2 source at the surface. So it's a lot more positive.
And day 5, we were at the Smith Rapids Bridge.
And then this was also, or like day 3, this was in the wake of a cold front too. So with the cooler air, so similar conditions as of day 3. And then as far as the meteorology goes, the meteorology between the sites was relatively consistent with a shallow inversion at ISS, but then well mixed all the way up to the boundary layers, which were also very similar at Smith Rapids.
And so the vegetation on this day was mainly aspen with some lowland opening, which could have been either just open grassy fields or a bog. Perhaps the standard deviation and range of the CO2 concentration were similar to other days.
And then the CO2 concentrations this day were slightly higher than the previous, and then the tall tower concentrations also remained relatively consistent throughout the morning. The Smith Rapids Bridge did have a lower reading than we initially measured at ISS as well.
Yeah, so for the WLEF tall tower, the CO2 fluxes were relatively consistent with what we would expect for 10 a.m. And then the difference in CO2, like Iman said, were also as expected, although it's pretty interesting that there is kind of like a slight peak at around 10 a.m. here compared to the other times around it. But then what is interesting is that with our Picaro measurements, we actually measured a very large negative CO2 flux at the surface, which indicates that there may have been a large CO2 sink. So we threw a lot of information at you. This is kind of like a summary table. I'm not going to go through every single point, other than just to kind of say that we had similar meteorological conditions between day 3 and 5, and also same vegetation, aspen, dominant vegetation, but we had really different surface CO2 flux values. So we had a very large and positive for day 3, whereas we had large and negative for day 5. So carbon source, day 3, carbon sink at day 5. So what does this mean? I guess we'll go into our conclusions now.
So to answer our question, how does CO2 concentration change over various kinds of terrain? We we found that there was more of a negative flux over aspen. The largest positive flux was over aspen and lowland opening. The second largest was over aspen and lowland conifer. And there was also a few sites we went to that were logging sites, so there was just piles of like dead aspen, which would likely contribute to a higher CO2 concentration. And then our next question, does meteorology impact that relationship? And we found that it does.
Yeah, and so to kind of summarize all of that, and to address our original hypotheses, we determined or figured that CO2 would vary or is varying across the terrain because we saw that there were these CO2 differences, but it may actually be largely due to meteorology. So even though the meteorological conditions were relatively similar between the days and the measurement sites, we were seeing these large differences in atmospheric CO2. So we actually have to probably hone in on kind of the subtle differences in the weak versus well-mixed time of, or like weak versus well-mixed boundary layers. So I guess our second point that the vertical mixing of the CO2 may be outweighing the uptake of CO2 by vegetation for days 3 and 4, but then the uptake of CO2 by vegetation may be dominating for day 5. That was when we saw the really large carbon sink at the ground. And then the CO2 source implies a weak mixing and the presence of a strong vertical gradient. So for days 3 and 4, that's what we essentially thought. There was large inversions on day 4, so yeah, it was pretty mixing. And then an alternative is that there could be higher concentrations of CO2 in these air masses that were being ejected into the surrounding environment, and we just happen to be chasing these really high CO2 air masses. But we would probably need to do more thorough analysis on that.
All right, but then as far as takeaways, what we all learned as a group on a more personal level, outside of the research, we all kind of agreed that patience pays off. This was quite a labor of love. It took our entire summer, but we're pretty proud of what we came up with, even if we didn't reach a super detailed and easy to pin down answer. With that, we'd like to open up for questions.
Thanks. Throw questions away.
Yeah, so I was curious when you said, meteorology had an impact on the
Yeah.
CO2 concentrations.
Yeah, sure.
On day 4, you said that was just prior to a cold frontal passage. Did you account for the effects, or was it necessary to account for the effects of any horizontal transport, either ahead of the front or behind it?
Right.
in
So
changing those values?
that's a really good question. I hadn't done that. I mean, there is, I think, a possible way of doing that. We unfortunately didn't get any measurements for after the storms that occurred, but yeah.
But you did have the remote sensing instruments. So
Yeah,
you
that is
could, in theory,
true.
use
Yeah.
the SONAR or RAS, the radar acoustic sounder, to get, or the, I don't know, or LiDAR to figure out mixing. But your idea is that you're essentially, if you're doing a Lagrangian budget and you're assuming all the fluxes are coming from the surface, then you're making, in theory, you've captured all the sources, right? But of course, and partly by having the actual windstorm tracks, the cool thing about the windsoms is they're lightweight and they're relatively staying in the boundary layer, so you're able to see the actual boundary layer trajectory of the air mass. You should be able to capture that. But
Yeah, we could get that. Yes.
Wouldn't you expect to see pretty strong negative correlation between carbon dioxide and humidity?
Yes.
And do you see that?
Have humidity profiles up. I did not.
Is it, it's towards the
But
end?
yeah, so let's do that extra slides.
Oh, it's past that.
Yeah.
So these extra slides look a little bit rough. Apologize, but yeah. So negative. Well, I guess we could even just consider what the mean relative communities were. Yeah, I did not look into that, but I guess for day 3, there was abnormally low relative humidities, and we saw large
Well,
positive.
I'm thinking
but-
when the plants, if the plants are taking up carbon dioxide, shouldn't they also be producing humidity
Yeah.
in a detectable way?
Yeah, you would expect transpiration to dominate.
Mhm.
Whether that, I mean, local humidity would be a function of both that and of course large scale dynamics, so hard to know for sure, but it's an interesting question.
There's another question. We've heard before that corn is different from other plants because the stomata stay open all day. And other plants shut down 10 o'clock in the morning or so. I didn't notice that in your detection here, that anything shut down after about 10 o'clock in the morning.
I mean, I think it was largely like forested areas where there were a ton of cornfields. So that might have just been like based on.
Well, yeah, I realize that, but what I'm saying is that supposedly normal plants, other than corn, shut down about 10 o'clock in the morning, but it doesn't look like anything shutting down.
That'd be a good question for further research.
Well, I mean, part of it here probably is, this is early July, the ground, it was pretty wet, right? You remember late June, early July around here was pretty wet. So there's probably no water limitation at all during this time period, I would guess. And I think the next intensive is in a week and a half from now. And we probably will see a different signal for sure.
So then what you're saying is this process of shutting down is a function of how much water these plants are smart enough to know to shut down, whereas I thought it was just, they always shut down 10 whether it's wet or not.
So if you don't mind me jumping in, if we want to go into plant physiology, the basic idea is that there are species that have adapted to be what are called isohydric or anisohydric, so it depends on whether they try to maintain a constant BPD gradient or whether they actually try to maintain water in the stem. Because what plants have evolved to do is primarily prevent cavitation, right? So what you want is you need that constant line of water from soil to leaf. And as soon as you have a hole in that, you get an embolism, right? And that's what's going to kill a plant eventually if you have too many of those in the
Right.
xylem. So it depends on the plant, but something like oak, which is like essentially like just uses the water whenever it wants, or corn is a C4 plant, versus something like some of the plants that are more conservative. It really depends on what they're adapted. So it's very species specific is the short answer.
But I think, Greg, what you're seeing is interpreting as shutting down is really just the growth of the daytime boundary layer, and you have a sharp gradient, you have high CO at night because it's inversion, and then you mix it. So I didn't see any evidence of anything shutting down, I just see evidence of daytime mixing and removal. Did you, so you consistently saw consistent signs of the fluxes between the tall tower and your measurements, but yours were 10 times larger. Was that, how did you determine your boundary layer height? That's one question. And did you do any intercalibration between your CO2 measurement and the tall tower measurements?
Yeah, so we determined the boundary layer heights from the potential temperature profiles from the wind sondes as well as relative humidity profiles. So pretty much everything from that was wind sonde, just very qualitatively estimated where the boundary layer height was. When we weren't able to use that, we looked at the QT soundings that were available every single day from the ISF. Okay, what's ISS? Yeah. And then for the intercalibration, we did not do that. No. Yeah.
But
Well, you
also,
also-
like, our measurements were at the surface and the tall tower was at a higher.
Yeah.
Yeah, one thing that we had looked at earlier was, the last point that is the vertical gradient. We do have some measurements of really good vertical gradient of CO2,
Right.
and that's almost certainly was, I think, driving.
And you see that strong gradient even with the tower.
Oh, yeah.
The lowest tower one's 50 meters, 30 meters. So what's between 30 meters and the surface?
So our other site, we had CO2 at 7 levels between 1 and 30 meters. That one, I think we were looking at like around 5 to 10 ppm gradients
Yeah.
which makes sense.
Which I did not apply that. I haven't yet.
So we talked about potentially correcting the data for gradient. But part of this is I would say, some of uncertainty. What was the average distance between your upland and downland sites?
Like, was it 10, 12?
Yeah, I actually wrote this down.
It's all from my map, but I'm gonna try and get that.
Okay,
up again.
around like 7,000 meters.
So you're talking pretty small gradients, right? Luckily, you had a nice instrument. So do you remember what the accuracy of your gas scouter is?
Ooh, it's like, 0.05 ppm.
It's probably its precision, but I guess its
Precision.
accuracy is about 0.2 ppm or so. It's pretty hard to do, actually. So,
Why did it go up so high when you were driving?
yeah, good question. I don't know.
When we were recording, while we were driving, we had the measurement tube for the Picaro aimed out the window. So if cars drove by, it's most likely due to the fact that everybody was like on the road.
Yeah,
Yeah.
that's a puzzle. Because you're in front of your exhaust, so.
Yeah, and there weren't too many cars, because you're northern Wisconsin, so I also wonder if it was, like, if soot remains in the air afterwards, or if there's like some wind component.
Residuals.
Yeah.
I bet you it's recirculation of your own breath.
I was wondering. It could be.
The 600 sounds like a typical concentration.
How is it determined is there a flow in and out of it?
There's a pump. And so it's sucking in air through a tube and a filter.
There must be some sort of a calibration on the radio which is sucking in, and if you guys are sort of pressure difference between the, as you're going along, you'll have a pressure difference on the top of the tube.
Could be. Yeah.
So you might have been sampling inside air at that point.
It's a possibility. It's a guess. I don't know for sure.
It was just kind of a experiment to find.
The other thing is you also, I think we looked at some of your boundary lines against the HSRL LiDAR, which is another really accurate way to look at the LDAP.
Yeah.
So that was a useful thing. Any other question?
I guess one last thing to comment on the boundary layer height. So we did the mean boundary layer height between the two measurement sites. And so we did notice that there was a difference in boundary layer height between the two, as even as large as like a couple hundred meters. And so just doing that average it does produce another uncertainty. So,
You're missing a treatment term.
yes.
Well, that brings up another thing too. When these other boundary layer studies, I know we've done in Florida, for instance, with Tammy Wickworth, one of the things they find is the dominance of roll vortices affecting the variability of things like humidity in particular. I don't think they're measuring carbon dioxide, but humidity. And the humidity can vary by 30–40% on a 5 or 10 minute frequency, just because of these rolls.
Yeah.
And you see those high frequency variations in carbon dioxide, since you do seem to have some source effect at the surface.
I don't know. Unfortunately, we didn't. I'm sure we could figure that out.
Well, you could look at the radioacoustics
Yeah.
after, right?
Yeah.
Humidity, and I think you do see these. I mean, that's one of the hypotheses we're going after is vortices that contribute to changes in the surface energy balance that we don't capture by standard tower flux measurements. I saw them on the aircraft for sure, as we were flying through them and felt them.
Yeah, I had a question. Can you go back to the slide where you compare the or the tall tower CO2 flux and the Picaro flux? So question, that's comparing the flux at the surface below the tall tower, or is that for the path or something?
So the WLEF is it's the 122 meter eddy flux just like at the tower. So that is the CO2 surface flux at the tower, but at 122 meters.
So-
And then Picaro is along the path.
Along the path. So you didn't do like, or whoever was doing car measurements, like circling around the tall tower, like using the Picaro, just to be like, what does it say right below the tower?
That would have been cool. We did not do that.
Yeah, and part of this is that even though they may have offsets in absolute measurements, I'm pretty confident in your relative CO2 concentrations to within half a part. So I guess my question in general would be, okay, well, let's say if it wasn't the last day of the summer semester, and then we decided that you should all go out for the second intensive for another week, what would you do differently, or how would you extend your experiment if you really wanted to keep testing this hypothesis?
Could walk around the bottom of that tower.
Okay, so Julia's suggestion. Other things you do differently about this particular summer?
You could have like 2 Picaros, that'd be cool, to do upwind and downwind measurements at the same exact time. So you could see if there were like low frequency eddies that traveled from one site to the other without having to worry about, okay, we have so much time, we have to get to a site that's close enough.
Just another $40,000.
Yeah.
But the one thing we do have that we didn't quite have access to yet was the 19 flux towers. Now we have the real-time data for. So in theory, you do actually have a little bit of that,
Yeah.
which we didn't have.
So how much data analysis could you do in real time? You just collect it and then do it later? So could your data analysis have been forming your collection?
Yeah, like mostly the only data analysis we did in the field was to calculate the boundary layer height and where we would launch our second wind zone. So like a distance downwind of the first one, and then everything else was afterwards.
But you could see the data in real time with the wind
Yeah.
sound, which is pretty cool. The same with Picaro. The Picaro uses Bluetooth, so you can just see the data on your phone as you're collecting it. Wi-Fi.
Yep.
Last question.
I have a question for anyone who wants to answer this. So I know that y'all won't get a chance to get to the fall IOP, the one that's happening
End of September.
End of September, okay. But if you were there and taking these types of measurements, what do you think might be different or change with the season? Or do you think that the end of September in North Wisconsin is basically?
Yeah, you're going in the fall there, so you're probably losing a lot of what we were having as a CO2 sink when we were here, because obviously it's in the summer, the leaves are all full, they're taking in lots of sun energy using photosynthesis. So I'd expect that the sinks of CO2 would be much, much less. I mean, end of September, maybe not so much, but as we move through October and November, definitely you'd see a decrease.
Cool. All right, let's give a hand. It's another good. We are collecting terabytes and terabytes of data, of observations and models on this. And as synoptic systems go through, mesoscale systems through, we've got Spark system from Science and Engineering. We have a couple of dial and Raman LiDAR doing water vapor measurements. We have 3 Doppler LiDARs doing wind measurements. We have 19 towers measuring meteorology at 20 times a second. Tons and tons of data, plus an aircraft flying for 80 hours over this domain measuring eddy fluxes and meteorology, and another Raman LiDAR and a cloud LiDAR. Anything that we want to make all this data public within 6 months, but you can get a lot of the data now and in real time. So if you're interested in getting like the real time updated every 5-minute RAS or radar data, or the sounding, the radiosondes are put online within 15 minutes of launch. During the IOPs, we launch them every 3 hours or so. Contact me, because there's way more data here than my lab will ever analyze in its entire career, and we want all of you to use